Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad bin Muhammad Said. So today for our group, we will present about the chapter 4, Trades and Concurrency. I will continue for the objective of this chapter. We need to identify the basic components of a trade and contrast trades and processes. Second, we need to describe the benefits and challenge of designing the multi-threaded application. Illustrate different approaches to implicit trading, including trades pool, port join, and grand central dispatch. And we need to describe how the Windows and Linux operating system represent trades. And lastly is designing multi-threaded application using the pthread, Java, and Windows trading APIs. As you know, the motivation of the chapter, most modern applications are multi-threaded. Trades is run within the application. Multiply tasks with the application can be implemented by the separate threads. For example, update display, fetch data, spell checking, and answer a network request. As we know, the process creation is heavyweight, while the thread creation is lightweight. Thread also can simplify the code, increase the efficiency, and we know that kernel are generally multi-threaded. Okay, I will continue for the single and multi-threaded processes. As we know that the single-threaded processes have only one thread of execution, and it can only perform a task one at a time. And for the multi-threaded process, we can see there are many threads in one processor, so it can process multiple tasks simultaneously at a time. For the multi-threaded, also will help the execution will be faster. Okay, for the multi-threaded server architecture, the client will send a request to a server for the process, and after the server receive the request, server will create a new thread to process the request, and after that, the main thread will continue receiving another additional client request, and after the thread is done with the server, done with the process, it will send response to the client and terminate the process, and the thread will be free and continue to receive another request from the server. For the benefits, firstly is responsiveness, may allow continued execution if part of the process is blocked, especially important for user interfaces. Second is resource sharing. Threads share resource of process and easier than share memory or message spacing. Economy, cheaper than process creation. Thread switching lower overhead than context switching. Scalability, process can take advantage of multi-core architecture. Multi-core programming. Multi-core or multi-processor system put pressure on programmer. Challenge includes dividing activities, balance, data splitting, data dependency, testing, and debugging. Parallelism is implies a system can perform more than one task simultaneously. Concurrency is support more than one task making progress. For single processor, scheduler providing concurrency. Okay, for the concurrency and parallelism, we know the concurrency execution on the single core system, you have the ability to make a progress on the multiple tasks at the same time. It can achieve by using a technique in a multitasking, where the CPU using the multiple thread of execution to do a different task simultaneously. And for the parallelism, is the ability to system to execute multiple tasks simultaneously. And as we know that the parallelism have the multiple core, so it using the multiple core to do the execution at the same time. This can lead a significant performance gains and will do the execution will much faster. Okay, for the types of parallelism, there is two is data parallelism and task parallelism. Data parallelism to distribute subset of the same data across multiple core. same operation on each. And task parallelism is distributing threads across core, each thread performing unique operation. Okay, for data and task parallelism, for the data parallelism, is a technique to distribute the data across the multiply processor or core to perform the same operation on each piece of data simultaneously. This will use when the data is too large fit into the single processor memory. And for the task parallelism, this involves dividing a larger data to a smaller task, each of which can be executed concurrently. This approach can be useful when the tasks are independent and can be executed in any order. Okay, for the AMDA law, this will identify the performance gains from adding additional core to an application that has both serial and parallel component. And this the formula for the AMDA law. I hope everyone already understand when because our doctor already explained in the class. I'll continue for the user traits and kernel traits. User traits is management done by user level traits library. Three primary traits libraries. First is POSIX P traits, Windows traits, and Java traits. Kernel traits support by the kernel. Example, virtually all general purpose operating system including Windows, Linux, Mac OS X, iOS, Android. Okay, for the user and kernel traits, for the user traits, it's managed entirely by the user level trait library for application. Is not using the operating system environment, and the kernel is not aware about the using thread and treats them as a single process with a single thread. And for the kernel thread is it's created and managed by the operating system, so the kernel is aware about the kernel threads and can schedule them independently and allow multiple kernel thread to execute concurrently on a different processor and process.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So now I'll be continue for the multi-threading models. There is three models: many to one to one, and many to many. For the first one, many to one, many user level threads map to single kernel thread, and one thread blocking causes all to block, and multiply threads may not run in parallel on multi-core system because only one may be in kernel at a time. Some of the examples are Solaris green threads and GNU portable threads. So in this model, a single kernel level thread supports many user level threads. As explained just now, context switching is extremely fast among the level threads. This model supports programmers that want to organize software as a group of concurrent threads. However, the kernel level thread can only execute in one CPU at a time. Therefore, the user level threads can only execute one at a time. True parallelism is not possible with this model. Also, if any of the user level threads makes a blocking system call, the kernel level thread will have to block, and so it will not able to run code for any of the user level threads until it gets out of its wait queue. And the net effect is that all user threads are blocked if any of them makes a blocking system call. So for the next one, uh, one-to-one model. In the one-to-one model, the number of kernel level threads is equal to the number of user level threads. Each user level thread has exactly one supporting kernel level thread, and each kernel level thread supports exactly one user level thread. If we use the one-to-one model, we cure the problems of the many-to-one model. Now, if one user level thread blocks the others, don't have to block. And also, user level threads can operate in parallel on a multi-processor. However, because each kernel level thread supports only one user level thread, we lose the advantage of quick context switches between user level threads. Also, each time we create a new user level thread, we need to create a new kernel level thread to support it. So we tend to use up more time creating threads. There is less flexibility to schedule the user level threads, and the scheduler in the kernel decides when to run the supporting kernel threads. This model may lead to excessive numbers of kernel level threads, which could adversely affect performance. Despite the disadvantages listed just now, many operating systems use the one-to-one model because it's relatively easy to implement, and the disadvantages are viewed as acceptable because many systems have a large number of processing costs that will support large numbers of kernel level threads. Next, the many-to-many models. In this many-to-many model, a set of user level threads is supported by smaller or equal number of kernel level threads. A user level thread is not necessarily bound to any particular kernel level thread. The thread library can reassign it. For example, if a kernel level thread X has to block, some of the user level threads that X was supporting can migrate for support to different kernel level threads. The many-to-many model can be seen as combining advantages of the many-to-one and one-to-one models. The many-to-many models allows the quick creation of a large number of user-level threads that can do very fast context switches. The application can have greater control over the number of kernel-level threads, and the application can control the scheduling of the user-level threads. So much of the advantage of the one-to-one model remains is the ability to exploit parallelism on a multiprocessor and independent blocking, and as well as the ability of one user level thread to block without forcing the other user level threads to block. And lastly, the two-level model. The two-level model is a variation on the many-to-many model, in which a user level thread may be bound to a kernel level thread. Uh, and it is difficult to implement the many-to-many model because just a few systems support it.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad FIKRI bin Muhammad Isa. So I will continue about the trade libraries. A thread is a lightweight of process and is a basic unit of CPU utilization, which consists of a program counter, a stack, and a set of registers. A process has a single thread of control where one program can counter and one sequence of instructions is carried out at any given time. Dividing an application or a program into multiple sequential threads that run in quasi-parallel, the programming model becomes simpler. The thread has the ability to share an address space and all of its data among themselves. This ability is essential for some specific applications. Threads are lighter weight than processes, but they are faster to create and destroy than processes. Thread libraries. Thread libraries provides programmer with API for creating and managing threads. There are two ways of implementing thread library, which is the first approach is to provide a library entirely in user space with kernel support. All code and data structures for the library exist in a local function called in user space and not in a system call. For the second approach is to implement a kernel level library supported directly by the operating system (OS). In this case, the code and data structures for the library exist in kernel space. Invoking a function in the application program interface for the library typically results in a system call to the kernel. The main thread libraries which are used are given below: POSIX threads, Win32 thread, and Java thread. So the next, pthreads. Pthreads may be provided either as user level or kernel level. A POSIX standard IEEE 1003.1c API for thread creation and synchronization specification, and it is not the implementation. API specifies behavior of the thread library. Implementation is up to development of the library. Common in Unix operating system, which is Linux and Mac OS X. So this is an example of the pthreads. There are two main types of thread libraries, which is user level and kernel level. User level thread libraries provide thread management entirely in user space without kernel involvement. This means that the library manages threads using its own scheduler and does not rely on the operating system scheduler. Examples of user-level thread libraries include pthreads, which is POSIX threads, Windows threads, and Java threads. Kernel-level thread libraries, on the other hand, rely on the operating system scheduler to manage threads. They provide a programming interface to create and manage threads at the kernel level, which allows for more efficient use of system resources. Examples of kernel-level thread libraries include Windows Native API and Linux kernel threads. Thread libraries provide many benefits to software developers. They allow for concurrent execution of multiple tasks, which can improve the overall performance of an application. They also provide a way to simplify complex programming tasks such as parallelizing algorithms and handling and synchronize input or output. However, thread libraries also introduce some challenges such as race conditions, deadlocks, and synchronization issues. Therefore, it is important for the developers to carefully design and test their multi-threaded applications to avoid these issues. Overall, thread libraries are an essential tool for developing high performance concurrent applications in modern computing environments. This is next. This is the also the example of the pthreads. The pthreads code for joining 10 threads. The Windows multi-threaded C program. So here is the coding for the Windows multi-threaded C program. This is also the example. And next is the Java threads. So the Java threads are managed by the JVM, typically implemented using the threads model provided by underlying OS. Java threads may be created by extending thread class. It is implementing the runnable interface. This is the, the example of the implementing the runnable interface. The standard practice is to implement runnable interface. So this is implementing runnable interface, creating a thread, and waiting on a thread. So we can see that the example for the three of the Java threads. Next is the Java executor framework. Rather than explicitly creating threads, Java also allows thread creation around the executor interface. This is an example for the Java executor framework. The executor is used as follows. This is also for the Java executor framework. Here, the execute use is the service dot executes and the column new task. So that's all from me. Thank you.
So for the next part is the implicit threading. Implicit threading is growing in popularity as numbers of threads increase. Program correctness is more difficult with the explicit threads, and the creation and management of threads are done by compilers and runtime libraries rather than programmers. For example of the implicit threading is thread pools, OpenMP, Grand Central Dispatch, and Microsoft Threading Building Blocks (TBB). Next is the thread pools. Thread pools create a number of threads in a pool where they wait for work. The advantages of the thread pools are they usually slightly faster to service a request with an existing thread than create a new thread. And next, it allows the number of threads in the applications to be bound to the size of the pool. And lastly, the separating tasks to be performed from mechanics of creating tasks allows different strategies for running tasks, such as tasks could be scheduled to run periodically. And these are some examples of the Windows API. Next is the OpenMP. OpenMP is a set of compiler directives and an API for C, C++, and Fortran. It provides support for parallel programming in shared memory environments, and it identifies parallel regions, blocks of code blocks of code that can run in parallel. And this is some of the example. Next is the Grand Central Dispatch. Uh, we short it by the name GCD. GCD is an extension to C and C++, available on Apple's OS X and iOS operating system to support parallelism. Similar to OpenMP, users of GCD define blocks of code to be executed either serially or in parallel by placing in a caret just before an opening curly bracket. GCD schedules blocks by placing them on one of several dispatch queues, and blocks placed on a serial queue are removed one by one, and the next block cannot be removed for scheduling until the previous block has completed. There are three concurrent queues, corresponding roughly to low, medium, or high priority. Blocks are also removed from these queues one by one, but several may be removed and dispatched without waiting for others to finish first. Depending on the availability of the threads. And internally, GCD manages a pool of POSIX threads which may fluctuate in size depending on the load conditions. So these are the two types of dispatch queues. First is the serial. It blocks removed in FIFO order. And queue is per process called main queue. And the second one is the concurrent. It is removed in FIFO order, but several may be removed at a time.
Next, threading issues. In this subtopic, we will talk about semantic of fork and exec system call, signal handling, thread cancellation of target thread local storage, and scheduler activation. Does fork? So the first one is semantic of fork and exec. Does fork duplicate only the calling thread or all threads? Some UNIX systems have two versions. One that duplicates all thread and another that duplicates the thread that invoke the fork. And the second one, exec. Exec usually works as a normal. It replaces the running process including all threads. The next one, signal handling. Signals are used in UNIX systems to notify a process that a particular event has occurred. A signal handler is used to process signals. The first one, signal is generated by a particular event. The second one, signal is delivered to a process. And the third one, and the signal is handled by one of two signal handler, which is default and use defined. Every signal has default handler that kernel runs when handling signal. User defined signal handler can override default. For signal threaded, signal delivered to a process. Where should a signal be delivered for multi-threaded? They should be delivered to a thread to the thread to which the signal applies, or to every thread in the process, or to certain threads in the process, and assign a specific thread to receive all signals for the process. So the next one is thread cancellation, terminating a thread before it has finished or completed. So we need to terminate a thread before it has been finished. A thread to be cancelled is called target thread. There are two general approaches, which is asynchronous and deferred. Asynchronous cancellation terminates the target thread immediately. Next is thread cancellation, terminating a thread before it has finished. It means that to terminate a thread, it must be before it has been completed. Thread to be cancelled is called target thread. There are two general approaches, which is asynchronous and deferred. Asynchronous cancellation terminates the target thread immediately, and deferred cancellation allows the target thread to periodically check if it should be cancelled, allowing it an opportunity to terminate itself in an orderly fashion. This is a code to create and cancel a thread. Next, invoking thread cancellation requires cancellation, but actual cancellation depends on thread state. From off, deferred, asynchronized. For off, the state is disabled. The type is there are no type. For deferred, the state is enabled and the type is deferred. Also same as asynchronized. If thread has cancellation disabled, cancellation remains pending until thread enables it. Default type is deferred. Cancellation only occurs when thread reaches cancellation point. For example, pthread underscore test cancel system call. Then after that, the cleanup handler is invoked. On Linux system, thread cancellation is handled through signal. And the next part, thread local storage. TLS allows each thread to have its own copy of data. It is useful when you do not have control over the thread creation process. For example, when using a thread pool. It is different from local variables. Local variable visible only during single function invocation. TLS visible across function invocations. It is similar to static data. TLS is unique to each thread. And the last one for this subtopic, scheduler activations. Both and two-level models require communication to maintain the appropriate number of kernel threads allocated to the application. Typically use an intermediate data structure between user and kernel threads, which is lightweight process, LWP. LWP appears to be a virtual processor on which process can schedule user thread to run. Each LWP attached to kernel thread, and how many LWPs to create according to the kernel thread. Scheduler activation provide upcalls. Upcalls is a communication mechanism from the kernel to the upcall handler in the thread library. This communication allows an application to maintain the correct number of kernel threads. So we move to the last subtopic of this topic, which is OS example. There are two types of, or as example, threads that is covered in this topic, which is Windows thread and Linux threads. The Windows threads, Windows implements the Windows API. API is application programming interface that is a set of defined rules that enable different applications to communicate with each other. Windows API is the primary API for the family of Microsoft OS. For example, Windows 10, Windows 7, Windows 11. Basically, a Windows application runs as a separate process, and each process may contain one or more threads. Additionally, Windows uses the one-to-one mapping, where each user-level thread maps to an associated kernel thread. The general component of a thread include a thread ID, uniquely identifying the thread, a set of registers representing the status of the processor, separate user and kernel stack for when thread runs in user mode or kernel mode, and lastly, private data storage area used by runtime libraries and dynamic link libraries (DLL). The register set, stacks, and private storage area are also known as the context of the thread. Next, there are three types of primary data structures of a thread, which is E-thread, K-thread, and TEB. E-thread, which is executive thread block that includes pointer to process to which thread belongs and to K-thread in the kernel space. Secondly, K-thread. K-thread, which is kernel thread block that includes shellcoding and synchronization information, kernel mode stack, and pointer to TEB in the kernel space. And lastly, TEB, thread environment block, that contains thread identification, user mode stack, and thread local storage in the user space. Next, as you can see in this figure, it shows about the connection between the primary data structure of the thread. The E thread and the K thread exist entirely in kernel space. This means that only the kernel can access them. And the TEB is a user space data structure that is accessed when the thread is running in user mode. Next is Linux threads. Linux refers to them as tasks rather than the threads. Thread creation is done through clone system call. Clone system call allows a child task to share the address space of the parent task, which is process. There are four flag control behavior for the clone system call. The first one is clone underscore fs, which means filtered file system information is shared. Second one is clone underscore vm, which means the same memory space is shared. The third one is clone underscore sighand, which means signal handlers are shared. And lastly, clone underscore files, which means set of Oppo files is shared. Struct test underscore struct points to process data structures, shared or unique. That's all from us. And the question can be viewed at our YouTube video description. Thank you.